Tonight, we're going to look at the nearest world that is slowly leaving us, the Moon. Every year, measured by laser beams sent from Earth and reflected back from the lunar surface, the Moon moves about 3.8 centimeters farther away. That is only an inch and a half, less than the width of two fingers, but stretched across millions of years. That small distance becomes a history of tides, rotation, impact scars, silent plains, and a companion world gradually widening its orbit above us. The Moon is not leaving in the way a ship leaves a harbor. It is leaving in the way a clock changes, one tick at a time. But what is actually happening between Earth and the Moon? And what kind of world is carrying that slow motion away? By the end of tonight, you're going to understand exactly why the Moon is receding, what its seas and craters really are, and why its quiet face is one of the best preserved records in the inner solar system. Before we get started, if you love exploring the Moon as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. The title sounds almost personal, as if the Moon has made a decision and is slowly turning away. But the real story is quieter and more physical. It is not intention, it is gravity. It is the motion of oceans, the turning of Earth, and the long arithmetic of an orbit. The distance added in a single year is smaller than many objects on a desk. A notebook is wider, a coffee mug is taller. Yet that narrow annual step is attached to a system 400 kilometers wide on average. A system old enough that tiny steps become geological handwriting. This is the first scale adjustment the Moon asks of us. Human attention is drawn to speed, brightness, and sudden change. The Moon's recession offers none of those. It is a fact that becomes meaningful only when the mind agrees to work with slow arithmetic. 1 year gives a finger's width. 1,000 years gives the length of a room. 1,000,000 years gives a distance you could drive in under an hour on an interstate. The number's humble, but it keeps going. Tonight's journey will begin with that measured widening. Then it will move across the Moon itself. The orbit, the phases, the face we know, the far side we did not see until the space age, the basalt seas, the highlands, the craters, the poles, the ice, and the objects humans left behind. The Moon is close enough to brighten a backyard and distant enough to be another world. It is familiar enough to name its shapes from memory, and strange enough that its dust still holds pieces of the early solar system. That is the scale of the story: close, far, known, still unfinished. The episode's title begins with motion, but the motion is only the doorway. Once that doorway is open, the Moon becomes a place rather than a symbol, a body with a radius of about 1,040 kilometers, a crust that differs from one hemisphere to the other, basins large enough to swallow countries, and a surface where a single footprint can outlast empires. To follow the Moon outward, we first have to understand the world that is moving. Its departure is not separate from its geology. The same early violence that made the Moon also shaped the tides that now move it away. The distance is measured in centimeters, but the meaning is measured in changed worlds and altered tides. The measurement that begins this story comes from lunar laser ranging. During the Apollo era, astronauts placed retro-reflector arrays on the lunar surface. These are not mirrors in the ordinary household sense. They are arrangements of corner cubes designed to send incoming light back toward its source with unusual precision. From Earth, observatories fire short laser pulses at the Moon, A tiny fraction of that light crosses the distance, strikes the reflector, and returns. The round trip takes a little more than 2.5 seconds because light itself needs time to cross the gap between worlds. By measuring that travel time very carefully, scientists can calculate the Earth-Moon distance with centimeter-level precision. It is one of the most elegant experiments in space science. A beam of light, a silent target, a clock, and a question repeated for decades. The answer is steady enough to be plain. The Moon is moving away from Earth at about 3.8 centimeters per year. Not meters, not kilometers, centimeters. The smallness matters because it keeps the story honest. The recession is real, but it is not a disaster unfolding on a human calendar. On the scale of a human lifetime, the Moon's orbit grows by a few meters. Over a century, it is less than 4 meters. Across 1,000,000 years, it becomes about 38 kilometers. Across hundreds of millions of years, the number finally becomes large enough to reshape the sky. That conversion is useful because it keeps the subject grounded. A rate can sound abstract until it is allowed to accumulate. The Moon's average distance is already so large that 38 kilometers barely changes the view. But time does not stop at 1,000,000 years. The Earth-Moon system has been evolving for billions. The small present rate is a snapshot of a long story, and the past rate was not always exactly the same because oceans, continents, and orbital conditions have changed. The Moon was once closer. In the deep past, it would have looked larger in the sky, pulled stronger tides, and moved through its orbit more quickly. Earth also rotated faster. The day was shorter. The system we know now is a later chapter, not the opening page. That is the first quiet lesson of the Moon. Even the familiar sky is historical. The distance overhead has not always been the same. The length of a day has not always been the same. The tide at a beach is part of a mechanism that has been changing for billions of years. When you see the Moon above a city roof or a dark field, you are seeing a relationship in motion. It is not motion that the eye can catch from night to night. It is motion that requires patience, instruments, and time deep enough to make inches matter. That patience is part of the beauty of lunar laser ranging. The experiment did not end when Apollo ended. The reflectors stayed where they were, and observatories kept asking the same question in the same language of light. Each measurement is small by itself. A pulse leaves Earth. A few returning photons are recorded. The result is added to a long series. Over decades, the series becomes a line clear enough to reveal the Moon's recession, Earth's wobble, and details of the lunar orbit. Science often looks like this at its strongest. Not a single grand announcement, but a careful accumulation of repeated measurements until the quiet pattern can no longer be missed. The present Moon sits, on average, about 238,855 miles from Earth, or about 384,400 kilometers. That number is an average because the Moon's orbit is not a perfect circle. It is slightly elliptical, so the distance changes as the Moon moves around Earth. At its nearer point, called perigee, the Moon is closer than average. At its farther point, called apogee, it is farther away. These changes help explain why some full moons look a little larger and some look a little smaller, though the difference is modest to the unaided eye. NASA often gives a useful scale. About 30 Earth-sized planets could fit between Earth and the Moon at the Moon's average distance. That is the strange spaciousness of the local sky. The moon feels near because it is our nearest large neighbor, but the room between is enormous. The moon itself has a radius of about 1,080 miles, or about 1,140 kilometers. Its diameter is a little more than 1/4 of Earth's. Its smallness is still planetary. It is not a lamp in the sky, but terrain wrapped into a sphere. The scale remains plain. That small world is not simply a silver disk. It has regions, histories, materials, and ages. The dark patches that early observers called seas are not water. The bright regions are not clouds. The round scars are not decorative markings. They are terrain. Even the word terrain changes the feeling. Terrain can be crossed, mapped, sampled, and misunderstood. Terrain has slopes and hazards. Terrain can be older in one place and younger in another. The moon's face becomes more interesting when it stops being an image and becomes geography. A dark oval is no longer just a mark. It is a mare. A pale rough zone is no longer blank brightness. It is highland crust. A circle is not a pattern. It is impact history. From the moon, Earth would dominate the sky. It would appear much larger than the moon appears from Earth, bright with oceans, clouds, and continents. For a person standing on the near side, Earth would hover in roughly the same part of the sky, turning slowly in place. The familiar illusion is that the moon is close enough to touch in thought. The truth is stranger. It is close in cosmic terms, but distant in human terms. Light crosses the gap quickly. A spacecraft needs days. A laser pulse needs seconds. A moving orbit needs ages. That middle scale is important. The moon is not a remote planet, but it is not a decoration attached to Earth. It is a world with its own gravity, its own rocks, its own interior, and its own long memory of events Earth has mostly erased. This middle scale is why the moon became humanity's first destination beyond Earth. It was close enough for a spacecraft to reach in days, close enough for radio signals to cross the gap in a little over a second one way, and close enough for a person on Earth to watch its shape change through the month. But it was also far enough that every landing required navigation, propulsion, life support, and a controlled descent onto unknown ground. The moon is the nearest test of being planetary rather than local. It is the first place where human engineering had to meet another world's gravity and dust. The reason the moon recedes begins with tides. The moon's gravity pulls on Earth. It pulls more strongly on the side of Earth facing the moon, and less strongly on the far side. The result is a stretching effect, a pair of tidal bulges raised through ocean and solid planet together. Earth rotates once in about 24 hours. The moon takes about 27 days to orbit Earth against the background stars. Because Earth spins faster than the moon travels, the tidal bulge is carried slightly ahead of the line between Earth and moon. That offset is the key. The bulge pulls gravitationally on the moon. Because the bulge is a little ahead, it gives the moon a small forward tug along its orbit. That extra orbital energy raises the moon into a slightly larger orbit. A larger orbit means a greater average distance from Earth. Energy and angular momentum are being redistributed within the Earth-Moon system. Earth gives up a little of its rotational motion. The moon gains orbital distance. Earth's days become very slowly longer. The moon's path very slowly expands. The number attached to that exchange is about 3.8 centimeters per year. The oceans make the effect visible, but the whole planet participates. Land flexes too, by smaller amounts. The solid Earth rises and falls under tidal forces. Water, rock, rotation, and gravity form one coupled system, not separate pieces politely ignoring each other. The ocean response is especially complicated because continents interrupt the flow. Tides slosh in basins, reflect from coastlines, concentrate in bays, and weaken in other places. That means the same lunar pull can produce very different local tides depending on geography. The global force is simple in principle, while the local tide table can be intricate. This is another place where the moon's influence becomes earthly, filtered through coastlines, seafloors, and the shape of a particular bay. This is not a leak into space. The moon is not taking energy from nowhere. The widening orbit is paid for by Earth's rotation. The day lengthens by tiny amounts over time. In ancient rocks and fossil tidal patterns, scientists find evidence of a younger Earth that spun faster. Some tidal rhythmite deposits preserve patterns that can be interpreted as ancient tide cycles. They suggest that hundreds of millions of years ago, there were more days in a year because each day was shorter. The calendar written in stone remembers a faster spinning planet. So the moon's departure is not separation in isolation. It is a trade. The moon moves outward as Earth slows down. The ocean tide under a pier and the length of a day on a wall clock belong to the same story. The same principle appears in old stone, modern tide gauges, orbital equations, and the laser measurements that keep refining the distance. Earth is active and self-editing. Ocean basins change shape as plates move. Coastlines migrate. Sediments bury older shores. Yet hints remain, and the moon supplies the external clock. Together, Earth and Moon form a coupled historical instrument. The tide is not only something that happens at beaches, it is a way for a rotating planet and an orbiting body to exchange motion over time. This is why the word leaving needs care. The moon is moving away, but not in a way that should make tonight's sky feel fragile. At 3.8 centimeters per year, it would take more than 26 million years to add about 1,000 kilometers to the average distance. A human life is not long enough to see the moon's face shrink because of recession. A civilization's written history is not long enough. Even the span since the first cities is only a small line on the scale required to make the change obvious. The recession will matter more in the deep future for eclipses and tides. Total solar eclipses depend on a delicate, apparent-size coincidence. The sun is about 400 times wider than the moon, and also about 400 times farther away, so their disks can appear almost the same size. As the moon slowly recedes, its apparent size decreases. Far in the future, the moon will no longer be able to cover the sun completely from Earth's surface. Total solar eclipses will give way to annular eclipses, rings of sunlight around a smaller lunar silhouette. Tides will also change, though not simply vanish. The sun raises tides too. Ocean basin shapes matter. Continents move. Coastlines shift. The future tide is not just today's tide made weaker by distance. It is a changing planet under changing geometry. That is why careful language matters when discussing the deep future. It is easy to imagine a single dial labeled tide strength and turn it slowly down. The real system has more dials than that. The Atlantic did not always have its present shape. The Pacific will not keep its present shape forever. Ice sheets come and go. Sea level moves. The moon's recession is steady enough to measure, but its effects pass through an Earth that is also changing. For tonight, the honest scale is this. The moon is leaving, and it is staying. It is moving away measurably, and it remains bound to Earth. Its slow retreat is not an omen. It is a record of the gravitational relationship that made our familiar world. That distinction protects the story from false drama. The moon is not slipping beyond reach in any ordinary sense. It is not about to leave Earth's gravitational family. It is not a clock counting down to a visible loss. The better feeling is subtler. The sky is stable enough for a lifetime and changing enough for a planet's biography. The moon can be constant in memory and variable in physics at the same time. That is often how astronomy works. It gives the eye a still image and gives the mind a process so large that stillness becomes only the first impression. The moon's orbit gives us two common numbers that are easy to confuse. Relative to the distant stars, the moon orbits Earth in about 27.3 days. But the cycle from one full moon to the next, or one new moon to the next, takes about 29.5 days. The difference happens because Earth is also moving around the Sun. By the time the moon has completed one orbit relative to the stars, Earth has traveled farther along its solar path. The moon needs a little extra time to line up with the Sun in the same phase again. That is why the month of phases is longer than the orbit measured against the stars. New moon, crescent, first quarter, gibbous, full moon, and back again are not changes in the moon itself. They are changes in geometry, sunlight, and the portion of the day side visible from Earth. There is always a day side and a night side on the moon, just as there is on Earth. The phrase dark side is misleading if it means a side that never sees sunlight. The far side receives sunlight. It has lunar mornings and evenings. It is simply turned away from Earth. While those phases repeat month after month, the whole orbit is quietly expanding at about 3.8 centimeters per year. That is much too small to alter the phase cycle in any ordinary lifetime. Yet it is the background motion beneath every crescent seen from a porch and every full moon over water. The phases have shaped calendars, planting traditions, navigation, and poetry. But physically they are simple. The moon is a sphere lit by the sun. We see different portions of the lit half as the moon moves around Earth. The beauty is not reduced by the geometry. It is made clearer. The same geometry also explains why eclipses are special rather than monthly. The moon's orbit is tilted by about 5 degrees relative to Earth's path around the sun, so most new moons pass above or below the sun from our point of view, and most full moons pass above or below Earth's shadow. Only when the alignments cross near the right nodes do solar or lunar eclipses occur. The monthly cycle sets the stage. The tilt decides when the shadow play happens. Sometimes the unlit part of a crescent is faintly visible. That glow is Earth shine, sunlight reflected from Earth to the moon and back again. In that dim gray light, Earth and moon briefly illuminate each other, two bodies exchanging brightness across the same gap that lasers measure. Nothing in the monthly cycle is hurried. The moon rises later each day because it has moved eastward in its orbit. Its changing shape is the visible clockwork of celestial motion. It is one of the few astronomical machines people can watch without instruments, night after night. The numbers behind that clockwork have names. The 27.3-day period is the sidereal month, measured against the stars. The 29.5-day period is the synodic month, measured against the sun-earth-moon geometry that creates phases. These names sound technical, but they describe familiar experience. A farmer marking moonlight, a sailor watching tides, and an astronomer planning observations are all working with the same moving geometry. The moon turns calendar, lamp, and measuring device into one object. It is the rare world whose orbital mechanics are written directly into ordinary life. The moon keeps almost the same face turned toward Earth because it is tidally locked. Its rotation period matches its orbital period. It turns once on its axis in the same time it takes to go around Earth once, so the same hemisphere generally remains in view. This locking did not happen by coincidence. Early in the moon's history, Earth's gravity raised tides in the moon's body. Internal friction dissipated energy and slowed the moon's rotation until the stable state was reached. One spin for one orbit, one familiar face toward Earth. The face is not perfectly fixed. Because the moon's orbit is elliptical and tilted, we see a little around the edges over time. This wobble, called libration, lets Earth-based observers view slightly more than half of the lunar surface across a month. Still, the far side remained unknown to human eyes until spacecraft. Before 1959, no person had seen it. People had mapped the near side for centuries with telescopes, naming seas and craters. But half the moon remained a hidden country. The far side is not the dark side in the literal sense. It is dark only to direct view from Earth. Sunlight reaches it, shadows cross it. Craters there experience day and night. The difference is not illumination. The difference is orientation. This correction is more than a vocabulary preference. Calling it the dark side can hide the real mechanism. The far side is not mysterious because it lacks sunlight. It was mysterious because the moon's synchronous rotation kept it facing away from Earth. A spacecraft had to go around the moon to see it. The phrase far side keeps the physics intact. It says where the hemisphere is, not what the sun is doing. On the near side, Earth would hang in the sky with only small motions. The person standing there would not watch Earth rise and set the way we watch the moon. The locked relationship would turn our planet into a luminous fixture above the black horizon. That is one reason the moon feels intimate. It has a face. Human beings notice faces even where none exist. But in this case, the pattern has a physical cause. The same dark Maria, the same bright highlands, the same old scars are presented to Earth again and again. The lock is another consequence of tides. Gravity does not only pull oceans. It shapes rotations. It couples bodies together until spin and orbit find a lower energy arrangement. The moon's familiar stillness in our sky is the fossil of an ancient adjustment. Other worlds show the same kind of gravitational discipline. Many large moons in the solar system keep one face toward their planets, including the Galilean moons around Jupiter. Tidal locking is not rare. What makes Earth's moon special to us is proximity and scale. It is large compared with Earth, larger in relative terms than most moons are compared with their planets, and it dominates our night sky. So a common gravitational outcome becomes emotionally distinctive here. The moon's steady face is not a painted mask. It is orbital history made visible every clear night. To understand why the moon exists at all, we go back to the young Earth. The leading theory says that a Mars-sized body, often called Theia, struck the early Earth more than 4 billion years ago. The collision blasted material into orbit, where debris gathered into the moon. This is not a small claim, so it is usually stated carefully. The giant impact hypothesis is the leading explanation, supported by many lines of evidence, but the exact details are still studied. Simulations vary. Isotopic measurements sharpen the problem. The moon's birth is known in outline, not every frame. The first moon was not the calm, gray world we see now. It was likely largely molten, heated by impact energy, accretion, and radioactive elements. Its surface may have been a magma ocean, a global or near-global layer of liquid rock slowly losing heat to space. As that magma ocean cooled, minerals separated. Lighter minerals rich in calcium and aluminum rose to help form the early crust. Denser materials sank. The process built a layered world. Crust above, mantle below, metal core deeper still, though much smaller proportionally than Earth's. Much of the moon's magma ocean may have crystallized within roughly the first 100 million years. That is early considering the solar system is about 4.6 billion years old. The moon became a record keeper while the inner planets were still being heavily reshaped. Those first 100 million years were not calm. The young solar system was full of leftover bodies, fragments, and unstable orbits. Worlds grew by collision. Surfaces melted, cooled, and were struck again. In that environment, forming a crust did not mean the moon became finished. It meant the moon had a surface on which later impacts, eruptions, and space weathering could begin writing. The archive started early, and then the archive was battered. Earth from that era has been recycled by plate tectonics, weather, oceans, and life. The moon did not have the same machinery. Its surface changed, but it did not erase itself as thoroughly. To look at lunar crust is to look at an older archive than Earth can easily offer. Theia itself is gone as a separate planet. Its material may be mingled with Earth and Moon. The name gives shape to a vanished body, a way to speak about a collision that helped create tides, months, eclipses, and the pale companion above every human generation. In that early system, the moon was closer than it is now. Tidal effects would have been stronger. Earth's day would have been shorter. The slow recession measured today at 3.8 centimeters per year is a late remnant of a relationship that began in heat, collision, and molten rock. The giant impact idea also explains why the moon is comparatively poor in volatile materials, why it is similar to Earth in some isotopic signatures, and why it has such a small iron core relative to its size. No single clue carries the whole theory. The strength comes from the way many clues point toward a violent shared origin. The moon is not a captured wanderer in the leading picture. It is kin to Earth, made from material connected to the early Earth and the impactor. That makes its recession feel different. The moon is moving away from the world whose early catastrophe helped create it. The moon's first crust is still visible in the bright highlands. These regions are older than most of the dark Maria. They are rich in minerals that formed when lighter materials floated upward through the cooling lunar magma ocean, building a pale anorthositic crust. Anorthosite is a rock made largely of plagioclase feldspar. On the moon, it is tied to the ancient highlands. Apollo astronauts brought back samples that helped confirm this story, giving scientists pieces of that early crust to study in laboratories on Earth. The highlands look brighter partly because of composition and partly because they are rough, cratered, and old. They were bombarded for billions of years. Their surfaces preserve overlapping impacts, basin rims, ejecta blankets, and broken rock, all layered like weatherless memory. When you look at the moon with the naked eye, the brighter areas are often highlands, and the darker areas are often Maria. This contrast gives the near side its familiar pattern. It is geology visible without a telescope, a map drawn in brightness. The early crust did not form evenly everywhere. Later measurements suggest the far side crust is thicker than the near side crust. That lopsidedness helps shape the different histories of the two hemispheres, including why the near side has so many broad dark plains. The lopsidedness is one of the reasons the moon rewards global mapping. From Earth, the near side could tempt us into thinking Maria are normal lunar surfaces. Once the far side was mapped, the near side became the unusual hemisphere in some respects. The dark plains are familiar because they face us, not because they dominate the whole moon. Familiarity and typicality are not the same thing. The highlands also carry the memory of the period when impacts were common across the inner solar system. Earth received impacts too, but erosion and plate tectonics have hidden most of that ancient surface. The moon kept more of its bruises, so the highlands are not empty gray background. They are old crust, old chemistry, old violence, and old cooling. They are the moon's first surviving face, a pale continent of time surrounding younger dark plains that arrived later. The brightness of the highlands can be misleading because it makes them look almost gentle from Earth. In close view, they are rugged and densely scarred. Their pale material has been pulverized, thrown, buried, and re-exposed by impacts over billions of years. Many highland rocks are not simple pieces of original crust, but mixtures broken and fused by later events. Still underneath the damage is the first great separation of lunar materials, light crystals rising, dense minerals sinking, and a new crust hardening under a sky that had never held air. Inside, the moon has layers: crust, mantle, and core. It is not a dead ball of dust. It is a differentiated body, meaning its materials separated by density and chemistry during its early molten state. Heavy material moved inward. Lighter material stayed above. The lunar core is proportionally smaller than Earth's core. Earth is a large, active planet with a strong magnetic field generated in its metallic interior. The moon's internal engine cooled more quickly. Its ancient magnetic story is complex, but it no longer has a global magnetic field like Earth's. NASA summaries give a useful contrast. The near side crust is about 40 kilometers thick, while the far side crust is about 60 kilometers thick. Those are approximate values, but the difference is important. The moon is not perfectly symmetrical inside or outside. The thinner near-side crust likely made it easier for molten basalt to reach the surface after large impacts made deep basins. The far side, with its thicker crust, did not flood with dark lava plains to the same extent. Interior structure became visible as surface geography. Apollo astronauts placed seismometers on the moon, and those instruments recorded moonquakes and impacts. Seismic data helped reveal the layered interior. Later missions and analyses refined the picture. The moon can be read by the way vibrations move through it. Moonquakes are generally weaker and less frequent than earthquakes, but they matter. They show the moon is not simply inert. Tidal stresses from Earth can flex the moon. Cooling and shrinking can create stresses. Even a quiet world has internal motion. Apollo seismometers recorded different kinds of signals, including deep moonquakes, shallow moonquakes, thermal events, and impacts. The details are technical, but the broad message is clear. The moon responds to stress. Its interior carries vibrations. Its quiet surface is not proof of absolute stillness. A body can be geologically subdued and still active enough to speak through instruments left on the ground. Gravity measurements also reveal hidden structure. Some lunar basins contain mass concentrations, called mascons, associated with dense basalt and crustal structure. Spacecraft orbiting the moon feel these uneven pulls, and their paths carry information about what lies below. The interior matters because every visible feature has roots beneath it. Basalt, plains, basin shapes, crustal thickness, and ancient magnetism are not separate topics. They are connected pieces of one cooling planetary body, small enough to freeze early, large enough to keep a deep story. This is why the moon belongs in planetary science, not just sky watching. It is a natural laboratory for how rocky bodies differentiate, cool, crack, and preserve evidence. Because it is smaller than Earth, it lost heat faster. Because it lacks plate tectonics like Earth's, it kept surfaces that Earth destroyed. Because it is near, its samples can be studied directly. The moon is not merely a satellite of Earth in the administrative sense. It is a compact record of rocky planet behavior, orbiting close enough for comparison and far enough to have followed its own path. The near side is the moon most people know. Its dark markings form the old imagined face, the rabbit, the figure, the pattern each culture has interpreted differently. Scientifically, those dark areas are mostly maria, wide basalt plains that fill ancient impact basins. The Latin names came from early telescopic observers who thought the dark, smooth areas might be seas. Mare means sea. Maria is the plural. Mare Tranquillitatis is the sea of tranquility. Mare Imbrium is the sea of rains. Mare Serenitatis is the sea of serenity. The names are poetic, but the material is rock. The maria are cooled lava, rich in basalt, often darker because of iron and titanium-bearing minerals. They are younger than many highland surfaces, though still ancient by human standards. A small telescope reveals that the smoothness is relative. The maria contain craters, ridges, rilles, domes, and subtle flows. They look smooth beside the battered highlands because lava once resurfaced them. They are plains made by fire, not oceans made by water. The near side has more large visible maria than the far side. That asymmetry is one of the moon's defining mysteries and one of its clearest lessons. A world can be small, airless, and quiet, yet still have hemispheres with distinct personalities. As this familiar face recedes at 3.8 centimeters per year, it remains the face we keep seeing because rotation and orbit are locked together. The moon is moving outward, but it is not turning away. Its departure happens while the same hemisphere continues to look back. That is one of the episode's central images, a companion world that grows more distant without changing its gaze. The phrase is poetic, but the mechanism is physical. Tidal locking controls orientation. Tidal transfer controls recession. The two are related through gravity and friction across deep time. The moon's face and the moon's distance are both products of interaction, not isolation. Early lunar maps were made by patient observers at telescopes, watching shadows reveal relief. Crater rims appeared as bright arcs. Mountains cast long shadows. The terminator, the line between lunar day and night, became a moving tool for reading topography. Near the terminator, low sunlight makes the moon look almost sculpted. Features that seem flat at full moon rise into relief. A crater wall becomes a ridge of light. A wrinkle ridge becomes a faint amber thread. The moon is best read sideways. This is why lunar observing changes with phase. Full moon is bright and visually complete, but its overhead lighting can flatten relief. Crescent and quarter phases reveal topography because shadows stretch across the ground. A feature can disappear into brightness one night and stand out with clarity the next. The moon is not changing its rocks at that pace. The sun is changing the angle of revelation. To study the near side with a telescope is to watch the same terrain become new through illumination. The Maria deserve their own correction because the old names still shape imagination. There are no water seas in Mare Tranquillitatis or Mare Imbrium. There are no waves, no shores, no tides crossing those plains. The seas are basalt, made by ancient volcanic flooding. The sequence is simple in outline. An impact excavates a basin. The moon's interior remains warm enough for magma to rise. Lava spreads across the low basin floor. It cools into dark basalt. Later impacts pepper the plain, but the broad, smooth shape remains. Apollo samples showed that mare basalts differ from highland rocks. They contain more iron and sometimes titanium. Their ages vary, but many mare flows occurred between roughly 4.2 and 1.2 billion years ago. That is a long volcanic chapter for a small world. Wrinkle ridges cross some maria like low frozen waves. They formed as basalt layers cooled, contracted, and adjusted under stress. The word sea becomes strangely useful if handled carefully. These plains do have waves, but they are waves of stone. Sinuous rilles mark ancient lava channels or collapsed lava tubes. They curve across the surface like dry rivers, though their flow was molten rock. On the moon, river-like shapes can exist without water, because geology often repeats patterns using different materials. The old sea names remain because science often keeps inherited language. We know better now, but the names carry observational history. The Sea of Tranquility is not a sea. It is a basalt plain with a name that remembers a time before spacecraft brought back stones. Those names also help turn the moon into a navigable mental landscape. A person can move from tranquility to serenity, from Imbrium to Crisium, from Oceanus Procellarum down toward the southern highlands. The map becomes a series of places rather than a pattern of spots. Once the names are attached to geology, they stop being quaint errors and become doorways into explanation. This contrast is beautiful when held plainly. Earth's seas move under the moon's gravity, helping push the moon outward. The moon's seas are motionless basalt, named by mistake, carrying no water at all. One set of seas pulls and rises. The other preserves ancient fire. The old sea names also reveal how human understanding advances without fully erasing its earlier language. We still say sunrise, although Earth turns. We still call the Milky Way away, though it is a galaxy seen from within. We still call the Maria Seas because the names became geography. Scientific language often carries fossils of perception inside it. The important thing is not to remove the poetry, but to place it on the correct foundation. The Sea of Tranquility becomes more beautiful, not less, when it is understood as a plain of ancient basalt beneath a black sky. Mare Tranquillitatis became the most famous lunar sea on July 20, 1969, when Apollo 11 landed there. Neil Armstrong and Buzz Aldrin descended to a basalt plain chosen for relative smoothness and safety. The site is called Tranquility Base The lunar module Eagle did not land on a beach or a shore. It landed on powdered rock, regolith, over basalt. Armstrong's first steps pressed into grains made by impact grinding, micrometeorite bombardment, and the slow breakdown of surface material in an airless environment. Those boot prints remain because there is no wind to erase them and no rain to soften their edges. They may be disturbed by future visitors or micrometeorite impacts, but they are not weathering away in the ordinary earthly sense. The moon remembers footsteps unusually well. Apollo 11 left more than footprints. Instruments, parts of the lunar module, a plaque, and a retroreflector array. That reflector still participates in the measurement of lunar distance. A landing site became part of a continuing experiment about the moon's slow recession. The Sea of Tranquility lies on the eastern half of the near side as seen from Earth. Its surface is not uniform. It contains subtle color variations, small craters, ridges and boundaries with neighboring terrain. A historic name sits on a complicated place. The samples collected there were basaltic, helping confirm that the Maria were volcanic plains. Human exploration turned a telescopic suspicion into laboratory evidence. The moon was no longer only something seen. It became something weighed, sliced, dated, and chemically measured. There is a quiet scale reversal in that scene. The moon, usually a light in Earth's sky, became a ground under human boots. Earth became the light overhead. The familiar relationship turned inside out, and the basalt sea stayed still beneath it. For the astronauts, the moon was not abstract. It was footing, dust, glare, checklist, radio delay, sample bag, and horizon. For scientists on Earth, it was a chance to connect field context with laboratory measurement. For everyone watching, it was a change in the category of the moon. The object that had always been looked at had become a place from which looking back was possible. Every measurement that finds the moon moving away by 3.8 centimeters per year also touches that human history. The same world that raises tides and keeps ancient craters also holds a small array of prisms placed by people who arrived in a machine made of aluminum, fuel, math, and nerve. Tranquility Base is small compared with Mare Tranquillitatis, and Mare Tranquillitatis is small compared with the whole moon. Yet the site has become one of the most meaningful coordinates beyond Earth. It joins scientific fact with cultural memory. The landing did not make the moon important. The moon was already important. But Apollo 11 changed the relationship by proving that a place seen for all of history could become a place visited by human beings. The basalt plain became both terrain and threshold. Mare Imbrium, the Sea of Rains, is one of the largest and most prominent nearside maria. It sits inside a vast impact basin whose formation reshaped a broad portion of the moon. The basin is hundreds of miles across, a scar so large it became landscape. When basin-forming impacts occurred, they were not ordinary crater events scaled up slightly. They excavated enormous volumes of crust, raised rings of mountains, spread ejecta across distant regions, and created low places that later lava could fill. The mountain arcs around Imbrium are basin rings, not mountains built by plate collision like the Himalayas. They are the uplifted and broken edges of impact architecture. On the moon, some of the grandest mountains are not products of continents pushing together, but of worlds being struck. After the Imbrium Basin formed, basalt flows later filled parts of its floor. The dark surface we see is therefore younger than the impact structure beneath. The visible sea is a later skin over a deeper wound. Around Imbrium sit famous features: Plato with its dark floor, the Apennine Mountains, Sinus Iridum curving like a bay, and smaller craters that help observers orient themselves. The nearside moon is a map of named details nested inside larger structures. Large lunar basins are measured in hundreds of kilometers. Many formed around 3.9 billion years ago, during a period when the inner solar system was still being heavily bombarded. The moon's face is not random texture. It is impact chronology made visible. A basin records stages: collision, excavation, rebound, collapse, flooding, cooling, later cratering. Each stage modifies the one before it. The result is a surface that looks still, but contains time stacked vertically and spread laterally. To cross Mare Imbrium in thought is to cross a place where impact and volcanism overlap. It is not merely a dark patch in the man in the moon. It is a basin, a lava plain, a mountain-ringed archive, and one chapter in the moon's unequal hemispheric story. The scale also helps correct a common mental image of impacts. Many people picture a crater as a neat bowl punched into a surface. Basin formation is far larger and more complicated. Rock is excavated, melted, uplifted, collapsed, and faulted. Rings form. The crust is thinned and fractured. Later magma can exploit the damaged structure. A basin like Imbrium is therefore both an event and an invitation to later geology. The impact opens the architecture. Volcanism writes across it. Mare Serenitatis, the Sea of Serenity, lies near Mare Tranquillitatis and Mare Imbrium, a rounded dark plain edged by brighter terrain. Its name suggests calm, but its origin is violent. Impact excavation followed by volcanic resurfacing and long exposure to space. Mare Crisium, the Sea of Crises, sits near the eastern limb of the moon as seen from Earth. It appears as a dark oval set apart from the central cluster of Maria. Because of its position, libration changes how much we see around its edges. Mare Fecunditatis, the Sea of Fertility, spreads across the southeastern near side. Like the other Maria, it is not fertile in the earthly sense. Its name belongs to old sky geography. Its surface belongs to basalt, impacts, and billions of years of exposure. Mare Nectaris, the Sea of Nectar, occupies another ancient basin. Its rings and surrounding features help scientists reconstruct the sequence of lunar events. The relative ages of basins, craters, and lava flows can be compared by counting impacts and reading overlaps. If a crater cuts across a lava plain, the crater is younger. If a lava flow covers part of a crater, the flow is younger. This is relative dating, one of geology's basic tools. On the moon, the lack of weather makes those relationships unusually readable. Relative dating does not require knowing the exact year at first. It asks for order: which feature came before which surface covers another, which ray lies on top. Then when sample ages or crater counts are added, the order can be tied to numbers. The moon is valuable because it offers both clear relationships on the surface and returned rocks that anchor some of those relationships in absolute time. The named seas form a network of dark regions: tranquility, serenity, rains, crises, fertility, nectar, clouds, moisture, and others. They are not identical. Each basin has its own shape, age, composition, and later history. A lunar atlas is therefore more than a list of names. It is a history of how people learned to turn light and shadow into geography. The near side became a place through repeated attention, first by eye, then by telescope, then by orbiting spacecraft and landed missions. Across all of these seas, the same correction holds. They are not water. They are basalt plains. Their poetry survives because the old names are beautiful, but their truth is stone. The moon's seas are ancient fire cooled into darkness. Moving from one mare to another is like crossing chapters in a single geologic book. Some basins are round and clear, others are irregular, merged or partly buried. Some flows are rich in titanium and appear slightly different in color through spacecraft instruments. Some surfaces are older and more cratered. Others are younger by lunar standards. The eye sees dark patches. The instrument sees composition. The geologist sees sequence. The moon offers all three at once. Between and around the Maria rise the highlands. They are older, brighter, rougher, and more heavily cratered. They are rich in calcium and aluminum-bearing minerals, especially the anorthositic crust that formed early as the lunar magma ocean cooled. If Mare basalt is the story of later lava, highland anorthosite is the story of the moon's first floating crust. The contrast is one of age and material. Dark plains tell of volcanic flooding. Bright highlands tell of cooling, crystallization, and relentless bombardment. The highlands are crowded with craters because they have been exposed longer. Every impactor that struck and left a mark added to an accumulating record. Later impacts cut across earlier ones. Ejecta blankets cover older terrain. Time becomes a layered surface. As the moon moves outward at 3.8 centimeters per year, these old highlands remain among the most stable visible records of early inter-solar system history. Earth's comparable surfaces have been folded, subducted, eroded, buried, and remade. The moon kept more of the first draft. The highlands can look harsh in close view. Slopes are softened by impact gardening, not by wind. Dust lies over broken rock. Crater rims degrade slowly under micrometeorites and thermal cycling. Nothing is hurried, but nothing is untouched. Thermal cycling matters because lunar surfaces heat and cool over long days and nights. Rock expands and contracts. Tiny cracks can grow. Micrometeorites add another constant source of alteration. Without air and water, the processes are different from Earth's, but different does not mean absent. The moon's surface is worked on by space itself. At the borders between highlands and Maria, lunar history becomes especially clear. Pale, rough terrain meets darker, smoother basalt. Older crust meets younger fill. The edge is not just a color boundary, it is a contact between two eras of the moon. The far side is dominated by highland terrain, partly because its crust is thicker and less easily flooded by mare basalt. The near side carries the familiar dark face. The far side carries more of the older pale crust. The moon has a front and a hidden old country. The highlands ask for slow attention. They do not have the instantly recognizable romance of named seas or Apollo landing sites, but they are the moon's ancient foundation, the pale material that makes the younger dark plains stand out in the first place. They also remind us that brightness is not youth. On Earth, a bright surface might suggest snow, sand, cloud, or fresh exposure. On the moon, the bright highlands are often older than the dark plains. The visual intuition reverses. Dark does not mean old shadow, and bright does not mean fresh. The moon teaches by making familiar categories unreliable. Its face is easy to recognize and difficult to read correctly until the history of magma, impact and space weathering is brought into view. Craters are the moon's most obvious language. A typical impact crater has a raised rim, a bowl or floor, and often an ejecta blanket of material thrown outward. Larger craters can have central peaks formed when the surface rebounds after impact. The impact process is fast and violent. An object traveling many kilometers per second releases energy in an instant. Rock behaves almost like fluid under the force. Material is excavated, melted, shattered, and thrown outward. Then the scene becomes still. Because the moon has no thick atmosphere, small and medium impactors reach the surface more easily than they would on Earth. Because it has no liquid water erosion and no active plate tectonics like Earth's, the scars last. The surface is a memory field. Earth has been struck too, but on Earth, craters are erased by rain, rivers, glaciers, vegetation, volcanism, sedimentation, and moving plates. Our planet is alive with erasure. The moon is comparatively still, so it preserves events our own world has hidden. Scientists use crater counts to estimate relative ages. A surface with more craters is generally older than one with fewer, assuming similar impact rates. When crater counts are calibrated with radiometric ages from return samples, they become a powerful tool for dating planetary surfaces. There are complications, of course. Secondary craters can form when debris from a large impact falls back to the surface. Different terrains can preserve craters differently. Small craters can be erased or overprinted more easily than large ones. But the method remains one of planetary science's central tools. It turns a scarred surface into a clock, imperfect but useful, especially when tied to samples. The crater record spans scales from microscopic pits in glassy grains to basins more than 300 kilometers across. Every size carries information about the population of impactors and the surface conditions at the time. The moon is a witness plate for space debris. Standing near a crater rim, you would see no trees, no water, no haze softening the distance. You would see the geometry of the impact almost naked. Rim, slope, shadow, floor, blocks, and the black sky above it all. This is why the moon's quietness matters scientifically. It is not emptiness, it is preservation. Each crater is a sentence in a long record of collisions, and the record survived because the moon lacks many of the processes that make Earth so habitable and so forgetful. There is a cost to that preservation. The same absence that keeps the record intact also makes the surface exposed. No thick air catches the small stones. No ocean hides the scars. No forest grows over the ejecta. The moon is a witness because it is vulnerable in a particular way. It receives the sky directly. Every small impact contributes to the regolith. Every large impact rearranges the surface. The archive is made by damage, and the lack of repair is what keeps it readable. Tycho is one of the moon's most striking craters. It sits in the southern highlands and is about 85 kilometers across. Around it stretches a bright ray system, visible across much of the near side during full moon, like pale spokes thrown over older terrain. Tycho is young by lunar standards. Its age is often estimated around 108 million years, though that estimate depends on whether certain Apollo 17 samples really came from Tycho ejecta. That caveat matters. The crater is young, but exact age deserves careful wording. The rays are bright because they expose fresher material. Space weathering gradually darkens and reddens lunar surface material over time. Younger ejecta can appear brighter against older ground. Tycho's rays are therefore not painted lines. They are thrown rock and dust, aging slowly in sunlight. An impact large enough to make Tycho scattered material over vast distances. Some ejecta may have traveled hundreds or thousands of kilometers. On an airless world with low gravity, debris follows long ballistic paths, landing far from the crater that launched it. Inside Tycho, the central peak rises from the crater floor. Terraced walls descend from the rim. These forms reveal the energy of the impact and the rebound of the target rock. Even in stillness, the shape remembers motion. The central peak is especially useful because it can bring deeper material upward. In a large impact, the target is compressed and then rebounds, lifting rock from below the original surface. That means a crater can act almost like a natural drill, exposing material that would otherwise remain buried. For lunar scientists, a beautiful landform is also a sampling opportunity written at kilometer scale. If the age estimate is near correct, Tycho formed when dinosaurs still lived on Earth. That comparison is not meant to inflate the drama. It simply aligns calendars. A crater that looks fresh on the moon can be older than almost everything humans call ancient. For backyard observers, Tycho is easiest near full moon when the rays stand out. Near the terminator, its relief becomes more obvious. It is one of the places where the moon's visual beauty and scientific usefulness meet in a single bright scar. Tycho also shows how the moon allows different time scales to overlap in one view. The crater may be about 108 million years old if the sample connection is correct, which is young on a 4.5 billion year lunar clock. Its rays cross older Mare and highlands. Its central peak exposes material lifted from depth. The full moon turns it into a visual landmark, but the landmark is also a relative age marker, a compositional clue, and a reminder that impacts did not stop when the moon's early violence faded. Copernicus is another prominent young crater, about 93 kilometers across, located in Oceanus Procellarum near the edge of Mare Imbrium. Its terraced walls, central peaks, and ray system make it a classic example of a complex lunar crater. Aristarchus is a prominent bright feature on the moon. The Aristarchus Plateau contains volcanic features, rilles, and varied materials. Its brightness makes it stand out even through modest telescopes, a pale mark on the darker terrain of the northwest near side. Oceanus Procellarum, the ocean of storms, is the largest of the named dark regions. Unlike many circular maria, it is irregular and sprawling. It contains younger volcanic plains and important features that help reveal the moon's prolonged volcanic history. Copernicus shows how impact craters become structured landscapes. The walls slump into terraces. The floor partially fills with impact melt and debris. Central peaks rise where compressed rock rebounds. A single collision creates mountains, plains, and glass. Ray systems are useful because they cut across the older terrain below. They reveal sequence. A bright ray over a dark mare must be younger than the mare surface. The moon's history can often be read by asking which feature lies on top. Near Aristarchus, sinuous channels such as Valles Schrotteri point to volcanic processes. The moon is often imagined only as an impact world, but volcanism is equally essential to its nearside story. Fire-filled basins, carved channels, and built subtle domes. Tycho, Copernicus, and Aristarchus are not isolated curiosities. They are part of a surface where relative youth is visible through brightness, sharpness, and rays. On the moon, young can still mean tens or hundreds of millions of years. That sentence is one of the keys to lunar thinking. Human history uses centuries as large units. The moon uses them as dust. A crater older than the dinosaurs can look fresh because there has been no rain, no roots, no rivers, and no plate boundary to dismantle it. Freshness becomes a local property of exposure rather than a sign of recent human-scale time. The moon rearranges the listener's sense of age. It makes 100 million years feel almost recent, and it does so without raising its voice. The surface material under every crater and mare is regolith, broken rock, dust, glass, mineral fragments, and tiny impact products. It is not soil in the earthly sense. There is no biology making humus. It is rock mechanically and chemically altered by space. Micrometeorites constantly strike the surface. Over time, they churn, break, melt, and mix the upper layers. This process is often called gardening, a gentle word for relentless, tiny impacts. The lunar surface is cultivated by debris rather than roots. Apollo astronauts found the dust clung to suits and equipment. Lunar grains can be sharp because there is no water or wind around them. They are fine, abrasive, and electrostatically troublesome. The surface looks soft from far away, but its dust is difficult material. The famous footprints are part of this regolith story. They remain because the grains hold shape in low gravity and because weather does not pass over them. But the surface is not frozen forever. Micrometeorites will slowly alter it, grain by grain. Regolith also contains glass formed by impacts and volcanic fire. Some beads are ancient records of the solar wind, trapping particles from the sun. The dirt underfoot is a scientific library in miniature, each grain carrying physical and chemical history. Human machines made new marks: rover tracks, scoop trenches, experiment footprints, disturbed dust around landing sites. These marks overlay billions of years of natural processes. They are extremely recent scratches on an old page. The thickness of regolith varies by terrain. Older surfaces generally have had more time to accumulate a thicker broken layer. Beneath it lies fractured bedrock, itself cracked and altered by impacts. The moon's outer skin is a product of repeated collision. To imagine walking there is to imagine soundless contact with ancient fragments. Each step would press into material older than civilization, older than mammals, older than forests in many places. The ground would be gray but not simple. Regolith is also practical. Any future lunar base must deal with it constantly. It can abrade seals, cling to suits, interfere with machinery, and enter habitats if not carefully controlled. At the same time, it may become a resource, providing oxygen bound in minerals, shielding against radiation, and material for construction. The same dust that preserved Apollo footprints could become part of future walls or landing pads. On the moon, the surface is not just scenery. It is problem, record, hazard, and raw material at once. Beyond the famous Mare are quieter plains and subtle volcanic features. A telescope may show a dark surface that looks nearly flat, but spacecraft reveal flow boundaries, low ridges, domes, and channels. The moon's calm face contains fine structure. Wrinkle ridges form where basalt plains were compressed, often because of cooling, loading, and the settling of basin floors. They are low, broad, and easy to miss under high sun. Under low sun, their shadows reveal long arcs across the Mare. Rilles can be straight, arcuate, or sinuous. Some sinuous rilles likely formed from flowing lava, perhaps in channels or tubes that later collapsed. They remind us that the moon once had moving molten material crossing its surface in organized paths. Lunar domes are gentle volcanic rises, sometimes with small summit pits. They are not towering cones like some earthly volcanoes. They are low shields and swells, evidence of lava that emerged quietly and spread across the surface. Across these plains, the moon continues outward at 3.8 centimeters per year. The number is almost absurd beside a basin hundreds of kilometers wide and lava flows billions of years old. That contrast is the point. The moon changes slowly, and still it changes. Some mare regions contain multiple flows stacked through time. A surface may look like a single plane, but represent repeated eruptions. New lava covers older lava. Later craters puncture both. Subtle color and spectral differences help spacecraft distinguish one unit from another. The quiet plains are where the moon teaches patience. They do not announce themselves with bright rays or famous footprints. They ask the observer to notice low relief, slight tone, curved ridges, and the difference between apparent emptiness and genuine simplicity. These subtler features matter because they show that lunar volcanism was not one event. It was a long, uneven set of processes shaped by heat, crustal thickness, basin structure, and chemistry. Some eruptions spread widely, others formed smaller features. Some channels may mark lava that once flowed with enough volume to carve or roof over its path. The moon's volcanic past was quieter than Earth's in some ways, without plate boundaries and water-rich explosive volcanism as we know it. But it was not minor. It painted much of the face we recognize. The far side entered human sight in 1959, when the Soviet Luna 3 spacecraft photographed it. The images were crude by modern standards, noisy, blurred, and incomplete. But they revealed something no telescope on Earth could show. The hidden hemisphere had a different face. Before Luna 3, the far side was a fact inferred from geometry, not a landscape seen by human beings. The spacecraft turned inference into image. A world known for all of human history suddenly doubled in visible geography. The far side had far fewer dark maria than the near side. It looked more heavily cratered, brighter, and more highland-dominated. This was not what many people expected from a simple sphere. The moon was lopsided in history as well as crust. On much of the far side, Earth is never visible. A person standing there would see stars, sun, and black sky, but not the blue planet, except near the edges where libration changes the view slightly. The far side is radio quiet relative to Earth. That shielding has made the far side interesting for future radio astronomy. The moon can block much of Earth's radio noise, creating a quieter place to listen to low-frequency signals from the universe. The same geometry that hid the far side also makes it valuable. Modern spacecraft have mapped the far side in extraordinary detail. The Lunar Reconnaissance Orbiter and other missions have turned the hidden hemisphere into topography, composition maps, illumination maps, and high-resolution images. The unknown country is now surveyed, though not yet familiar to the public imagination. The far side changed our understanding of the moon because it showed that the near side is not the whole story. The face in the sky is only one hemisphere, the one pointed toward Earth by tidal locking. The other half keeps a different record. There is a psychological shift in that moment. For thousands of years, humanity had lived with a moon that seemed fully available to sight because its near side was so present and so detailed. Then a spacecraft showed that familiarity had been partial. Half the world had been hidden in plane geometry. This is a recurring lesson in exploration. The known face of a place can become so familiar that it disguises the existence of the unseen half. Luna 3 did not make the far side important, it made our ignorance visible. The far side differs partly because its crust is thicker. A thicker crust made it harder for basaltic magma to flood the surface after impacts. That is why the far side has fewer broad dark plains and more bright highland terrain. This does not mean the far side had no impacts. It had many. But after impacts excavated basins, lava did not fill them as extensively as on the near side. The result is a more cratered, highland-rich hemisphere with fewer dark volcanic plains. The reasons for the crustal asymmetry are still studied. Ideas involve the moon's early thermal evolution, the influence of Earth, and differences in radioactive heat-producing elements. The broad fact is clear: near side and far side cooled and evolved differently. The far side also contains enormous impact structures, including the South Pole-Aitken basin. It is not merely a blank back surface, it contains some of the most important lunar geology, much of it hidden from direct Earth view until spacecraft arrived. The asymmetry gives the moon a narrative shape. The near side is the face of Maria and human landing sites. The far side is the face of thicker crust, fewer seas, and deeper old scars. Together they make one world more complex than the silver disk suggests. The limb, the edge of the moon seen from Earth, is the border between those mental worlds. Along that edge, libration lets us peek slightly around the curve, enough to remind observers that the visible disk is not the whole body. Spacecraft completed that reminder. The moon is round in the obvious way, but our relationship with it has often been flat. One face, one view, one familiar pattern. When you imagine the moon leaving Earth, it is easy to imagine the visible face receding, but the far side is carried away too. The hidden craters, the thicker crust, the landscapes that never look directly at us. The whole moon moves. That whole world view is important because the moon's story is often told from Earthward perspective. We name the near-side seas because we saw them first. We place Apollo sites at the center of cultural memory because people went there. But the moon does not rank its hemispheres by our attention. The far side is not a backstage wall. It is half of the body with its own basins, crustal story, and scientific value. The moon is a sphere, and every sphere has more truth than its visible face. The South Pole-Aitken Basin is the moon's largest impact feature, spanning more than 2,500 kilometers across the far side and southern polar region. It is so broad that it occupies a substantial fraction of the lunar hemisphere. NASA describes the basin as about 10 kilometers deep on average, though its structure is complex. Its size makes it one of the largest known impact basins in the solar system. It is not a crater you can easily picture from ground level because it is too vast. The impact that made South Pole-Aitken excavated deep lunar material and reshaped a huge region. Studying it may help scientists understand the moon's mantle, early impact history, and the chronology of basin formation across the inner solar system. Because the basin is on the far side, it was unknown in detail before spacecraft mapping. Its discovery and study belong to the era when the moon stopped being only the near-side face and became a complete globe. A basin more than 2,500 kilometers across is difficult to hold in ordinary imagination. It is wider than the distance from New York to Denver. On the moon, such a feature is not a local landmark. It is regional architecture. South Pole-Aitken is also old. Later craters pepper its floor and edges. Its original form has been modified by billions of years of impacts. Like so much on the moon, it is both a single event and a surface that continued accumulating history afterward. This nested history is one reason lunar maps can feel dense. A basin contains craters. Craters contain smaller craters. Ejecta from one event crosses the remains of another. A later impact can sample an older basin floor and scatter pieces across new terrain. The surface is not a clean sequence of separate chapters. It is more like a manuscript where later writing presses into older ink without fully erasing it. Samples from this basin are scientifically attractive because they could help pin down the timing and nature of large impacts. A rock from the right place could connect lunar chronology to the wider story of Earth's early environment and the bombardment of the inner planets. The basin gives the far side its deepest scale anchor. It is a reminder that the moon's hidden hemisphere is not secondary. Some of the most consequential lunar records lie where ancient human eyes could never look. Because South Pole-Aitken is so large and old, it is not visually simple. Later craters, volcanic patches, ejecta from other impacts, and billions of years of space weathering complicate the original structure. That complexity is precisely why it matters. A clean, untouched basin would be easier to describe, but the real moon is a layered place. The basin records an enormous early impact and then records everything that happened to that region afterward. It is archive upon archive, a deep feature carrying a long afterlife. The poles bring a different kind of lunar geography. Because the moon's axis is only slightly tilted relative to its orbit, sunlight reaches the polar regions at very low angles. Some crater floors near the poles remain in permanent shadow. These permanently shadowed regions can become cold traps. Molecules that wander into them may stay for very long periods because temperatures are extremely low. Water ice can survive there in places where sunlight never reaches the ground. The contrast can be sharp. A ridge may receive long periods of sunlight, while a nearby crater floor remains dark and intensely cold. This makes the poles valuable and difficult. Energy may be available near some high spots, while ice may be hidden in shadow. The ice is not a lake, not a frozen sea, and not a smooth skating surface. It is mixed with regolith in cold, dark places. Its distribution varies. Some deposits may be patchy. The language has to stay careful because the moon is dry compared with Earth. NASA's LCROSS mission, paired with observations from other spacecraft including LRO, helped confirm water ice in permanently shadowed lunar polar regions. LCROSS deliberately impacted near the lunar South Pole in 2009, and instruments detected water and other materials in the plume. The Lunar Reconnaissance Orbiter maps temperature, topography, illumination, and surface properties. For the poles, this matters because a few degrees of slope can determine whether sunlight reaches a place and whether volatile molecules can survive nearby. Water ice matters scientifically because it records delivery and movement of volatiles. It matters practically because future missions may use it for drinking water, oxygen, or rocket propellant. But every practical statement depends on accessibility, concentration, and engineering difficulty. The moon's poles are therefore not simply destinations. They are test cases in working with extreme light and shadow. A base near the South Pole would need to manage power, thermal conditions, terrain hazards, communication, and the careful extraction of resources without assuming abundance. Even here, in the coldest lunar shadows, the wider Earth-Moon system keeps changing at 3.8 centimeters per year. The ice sits in darkness while the orbit grows by a finger's width annually. One process is local and frozen. The other is orbital and patient. The poles make the moon feel less like a single gray desert and more like a world of environments. There are hot sunlit plains, cold shadowed basins, bright highlands, dark Maria, and places where ice may have waded through immense stretches of time. This variety matters for future exploration. A mission near the equator faces long cycles of day and night. A polar mission may find places with more favorable illumination nearby, but also dangerous shadow, rough terrain, and communication challenges. Ice changes the strategic map, but it does not make the moon easy. Every resource on the moon comes with the cost of extracting it in vacuum, dust, radiation, and extreme temperature. The poles are promising because they are difficult in scientifically useful ways. The moon does not have breathable air. It has a very thin exosphere, a sparse collection of atoms and molecules so spread out that they rarely collide. Calling it an atmosphere without explanation can mislead. It is real but extremely tenuous. Particles in the lunar exosphere come from several sources: solar wind, micrometeorite impacts, radioactive decay, and atoms released from surface materials. Some are lost to space, some return to the surface. The system is delicate and thin. For a human being, the practical fact is simple. The moon's exosphere offers no pressure support, no oxygen, and no protection like Earth's atmosphere. A person needs a spacesuit or a sealed habitat. The black sky remains black even in daylight because there is almost no air to scatter sunlight. The absence of a thick atmosphere also means small meteoroids can reach the ground. On Earth, many burn as meteors. On the moon, they strike the surface, contributing to regolith gardening and constant microscopic change. Solar wind reaches the lunar surface directly, implanting particles in grains and affecting surface chemistry. Over time, this contributes to space weathering, the gradual alteration of exposed material. A rock lying on the moon is not under weather as Earth knows it, but it is not untouched. Without air, shadows are stark and sound cannot travel through open space. Heat moves differently. Dust behaves differently. The moon's serenity in images partly comes from absence. No clouds, no blue sky, no wind, no rain. But absence is an environment, not a blank. The exosphere is a reminder to avoid absolute simplifications. The moon is not airless in a perfectly mathematical sense, and it is not atmospheric in the way Earth is. The truth sits between easy phrases, as many good planetary truths do. That sparse boundary also makes the moon a place where surface and space almost touch directly. On Earth, the atmosphere mediates nearly everything. It carries sound, weather, scent, and clouds. It burns meteors and spreads heat. On the moon, the surface faces the sun and the solar wind with little mediation. A rock can sit under direct radiation for ages. A molecule can hop across the surface and vanish. The boundary between ground and sky is not a blue layer. It is nearly immediate contact with space. Temperature on the moon is severe because there is little atmosphere to move heat around. In sunlight, the surface can become very hot. In shadow, it can become extremely cold. The contrast depends on location, time of lunar day, and whether sunlight ever reaches the ground. A lunar day is long. Because the moon rotates once per orbit, a location on the moon experiences roughly 2 weeks of daylight followed by roughly 2 weeks of night. That slow cycle gives the surface time to heat and cool dramatically. For machines, that cycle is a serious design problem. Solar power is plentiful during the long day and absent during the long night unless a site has special illumination conditions. Batteries, nuclear power, thermal storage, insulation, and careful site choice all become part of survival. The moon's calendar is not only an astronomical fact, it is an engineering constraint written into every surface mission. Images from Apollo show harsh light and deep shadow. The sun is unfiltered by thick air. A white object can be glaring, while a shadow beside it is dark. Human explorers had to read terrain in conditions that were visually beautiful and operationally difficult. At the poles, permanent shadow creates some of the coldest known places in the solar system. Those cold traps are scientifically valuable because they can hold molecules over long periods. They are also difficult places to enter, power, image, and sample. The moon is calm in the sense that it has no storms, no thunder, no oceans beating against cliffs, but it is not gentle. Vacuum, radiation, dust, thermal extremes, and micrometeorites make the surface a severe place for machines and bodies alike. This contrast helps explain Earth's rarity. Our atmosphere softens temperature swings, moves water, burns many meteoroids, and scatters sunlight into a blue sky. The moon shows what rock looks like when most of those protections are absent. The quiet appearance of the moon can hide these physical conditions. From Earth, moonlight feels cool and gentle. On the surface, sunlight is direct, shadow is cold, and the horizon is close because the moon is small. That close horizon changes the feel of the world. Because the moon's radius is much smaller than Earth's, the surface curves away more quickly. The visible distance to the horizon for a standing person is only a few kilometers, depending on height and terrain. Mountains and crater rims can appear stark against blackness. There is no blue atmospheric distance to make far things fade. Space begins at the ground. The result is a landscape that can look both intimate and severe, a small world under an endless sky. Humans landed on the moon 6 times between 1969 and 1972. Apollo 11, 12, 14, 15, 16, and 17. All 6 landings were on the near side, partly because direct communication with Earth was simpler and safer. Each landing site visited a different kind of place. Apollo 11 went to Mare Tranquillitatis. Apollo 12 landed in Oceanus Procellarum. Apollo 14 visited the Fra Mauro Formation. Apollo 15 explored Hadley Rille. Apollo 16 went to highlands near Descartes. Apollo 17 reached Taurus Littrow. The Apollo missions returned 842 pounds of lunar material, about 382 kilograms. Those samples transformed lunar science. They allowed radiometric dating, chemical analysis, mineral studies, and direct comparison between mare basalts, highland rocks, breccias, and regolith. The missions also left instruments, including seismometers and retroreflectors. They left descent stages, tools, rover tracks, flags, and other artifacts. The landing sites are now historical landscapes as well as scientific locations. The flags have often been discussed, but the more lasting image may be the tracks. Wheels and boots mark the regolith. The marks connect human motion to a surface that otherwise changes by micrometeorites and impacts, not by wind or footsteps. These samples are still studied today, with instruments far better than those available in the 1970s. That was part of the wisdom of returning more material than could be immediately understood. A rock collected once can keep answering new questions for generations. At 3.8 centimeters per year, the Moon's recession across the entire Apollo era is only a little over 2 meters. The landing sites have not meaningfully receded from us in any emotional sense, but the measurement has continued year after year through the reflectors left behind. The human artifacts are young beyond measure compared with the rocks around them. A boot print from 1972 sits on regolith, made from materials billions of years old. Human history occupies a thin surface layer on lunar time. The landing sites also form a carefully chosen sampling strategy. Apollo did not simply repeat the same terrain 6 times. Each mission expanded the scientific reach. Mare plains, highlands, impact formations, rilles, valley settings, and varied rock types. The astronauts were trained as field observers because the context of a sample matters. A rock is more valuable when its position, surroundings, and relation to nearby features are known. The Moon became a field site, and the astronauts became geologic witnesses under extreme constraints. The samples taught scientists that the highlands are ancient and anorthositic, supporting the magma ocean model. They showed mare basalts came from volcanic activity. They helped calibrate crater counting, turning the Moon into a reference surface for dating other worlds. Radiometric dating of lunar rocks gave absolute ages to surfaces that could also be counted by craters. This pairing is powerful. Once scientists know the age of a sample's surface, crater density there can help interpret unsampled terrains across the Moon and beyond. Many lunar rocks are breccias, mixtures of fragments welded together by impact processes. They are records of violence assembled from older pieces. A single sample can contain materials from multiple events, making it both useful and difficult to interpret. The Moon also helps reconstruct the early bombardment of the inner solar system. If large impacts were common at certain times, Earth would have shared that environment. The Moon's preserved surface gives clues to conditions our own planet experienced, but mostly erased. This matters for understanding early Earth and possibly the origin and survival of life. Heavy impacts could destroy local environments and also deliver materials. The timing, frequency, and scale of impacts are not abstract lunar trivia. They belong to planetary habitability. The Moon is therefore a planetary archive. Its value is not only that it is close, it is that it is close and old, accessible and preserved, familiar and alien. A sample from the Moon can speak about Earth precisely because Earth has forgotten so much. Some Apollo samples were deliberately stored unopened for decades, waiting for better tools and better questions. That patience mirrors the Moon itself. Not every answer has to be taken at once. Some records are kept until a future mind is ready to read them. The Moon's chronology also supports studies of Mercury, Mars, and asteroids. Cratered surfaces across the solar system can be compared cautiously using the Moon as a calibrated reference. The nearest world becomes a measuring tool for many worlds. That is one reason the return samples remain more than museum objects. They are anchors. Without laboratory ages, crater counts would be more uncertain. Without mineral chemistry, the bright and dark terrains would be easier to misread. Without sample context, theories of magma ocean cooling, mare volcanism, and impact history would float with fewer constraints. The moon gave pieces of itself to Earth, and those pieces became a scale by which scientists measure surfaces no human hand has touched. The deep future returns us to the opening motion. The moon's orbit will continue to widen for a very long time, though the exact future depends on complex tidal evolution, continents, ocean basins, and the sun's own long-term changes. Simple extrapolation is tempting, but caution is better. Earth's rotation will continue to slow as angular momentum moves outward through tides. Days will become longer by tiny amounts. The moon will continue gaining distance. The familiar number remains the present measured rate, about 3.8 centimeters per year. Total solar eclipses will eventually become rarer and then impossible from Earth, because the moon's apparent disk will become too small to cover the sun completely. That future is remote, but it shows how a centimeter-scale annual change can alter a celestial spectacle. The present eclipse era is a temporary coincidence in the life of the Earth-Moon system. Earlier, when the moon was closer, it would have covered the sun more generously. Later, when it is farther away, the fit will be lost. We live in the interval where the match can be exact enough to reveal the solar corona around a black lunar disk. That is not a permanent property of the sky. It is a chapter. Tides in the far future will not be today's tides simply reduced. Continents move. Ocean basins open and close. Sea levels change. The sun's tides remain. The Earth-Moon system evolves inside a planet that also evolves. The future shoreline is not a fixed stage. The moon is not expected to vanish from the sky on any human or civilizational timescale. Its recession is far too slow for that. The phrase "leaving us" is emotionally true only when translated into deep time. It is a widening companionship, not an immediate farewell. In the distant past, the moon looked larger. In the present, it is just the right apparent size for total eclipses. In the far future, it will look smaller. The sky has eras, even when a single human life sees only one version. Future observers, if they continue measuring, will see the same principle. Light sent outward, light returned, distance calculated. The experiment is almost ceremonial in its simplicity. Ask the moon where it is. Wait 2.5 seconds. Read the answer. The deep future does not make tonight's moon less ours. It makes it more interesting. The white disk above the horizon is not a static ornament, but a moving participant in Earth's history, a companion whose distance is part of the reason our planet spins as it does. The far future also reminds us that astronomy is not only about distant galaxies and exploding stars. Sometimes the most profound time scale is attached to the object that rises over familiar rooftops. The moon is ordinary in the sense that people have always seen it. It is extraordinary in the sense that its ordinary presence contains billions of years of changing distance, changing tides, changing days, and changing skies. The everyday object is carrying deep time in public view. We have talked about the measured widening of the orbit, about laser pulses crossing the dark and returning from small reflectors left on gray dust. We have talked about 3.8 centimeters per year, a number so small it can sit between two fingers, and so persistent it can reshape deep time. We have talked about tides not just as water rising at a shore, but as the visible surface of a gravitational exchange. We have talked about Earth's rotation giving a little of itself to the moon's orbit, about days lengthening and distance increasing by patient degrees. We have talked about the orbit and the phases, about the difference between 27.3 days around Earth and 29.5 days from one full moon to the next. We have talked about sunlight, geometry, crescents, earth shine, and the monthly clockwork visible without instruments. We have talked about synchronous rotation, the reason one lunar face generally stays turned toward Earth. We have talked about the far side, not a dark side, but a hidden hemisphere that sunlight reaches and earthbound eyes could not see until Luna 3. We have talked about the moon's likely birth from a giant impact involving early Earth and a Mars-sized body called Theia. We have talked about molten rock, a cooling magma ocean, floating minerals, and the bright highlands that preserve some of that first crust. We have talked about the seas that are not seas: tranquility, rains, serenity, crises, fertility, nectar, and the ocean of storms. We have talked about basalt, ancient lava, old names, and the way a mistaken word can remain beautiful after the science changes. We have talked about craters as memory, about Tycho's bright rays, Copernicus and Aristarchus, central peaks, ejecta blankets, and the moon's ability to keep scars that Earth would have softened, buried, or erased. We have talked about regolith, sharp dust, boot prints, rover tracks, Apollo samples, polar cold traps, water ice, the thin exosphere, harsh sunlight, deep shadow, and the enormous South Pole-Aitken basin spread across the far side like an old hidden wound. We have talked about the moon as a place where contradictions can sit together without canceling each other. It is dry, yet it holds ice and shadow. It is quiet, yet it records violence. It is familiar, yet half of it was unseen until 1959. It is close, yet the distance between Earth and Moon can hold 30 Earths. It is leaving, yet it remains bound. Those paired truths are not decorations around the science. They are the science, translated back into human scale. So what does it mean that the moon is slowly leaving us? The honest answer is that the moon is receding because Earth and moon are locked in a tidal exchange. The moon raises tides. Earth's rotation carries those tidal bulges slightly ahead. Gravity pulls. Angular momentum moves outward. The moon gains orbital distance while Earth gives up a small amount of spin. That is the mechanism underneath the poetry. Not abandonment, not danger in the night sky. A physical relationship operating continuously, changing both bodies by amounts that become meaningful only when time is allowed to be immense. In that sense, the moon is leaving because it is connected to us, not because it is separate from us. The same gravity that lifts the oceans also moves the orbit. The same relationship that gives Earth tides slowly widens the space between the two worlds. The title is true, but it needs the scale restored. The moon is slowly leaving us in the way mountains rise, continents move, stars age, and days lengthen. Too slowly for alarm, too steadily to ignore. It is departure written in centimeters, not footsteps. And the world being carried outward is not empty. It holds basalt seas named by old observers, highlands from a cooling magma ocean, craters from vanished impactors, polar shadows where ice can endure, and human artifacts so young they almost belong to the present tense. The moon keeps the same face generally turned toward Earth while it recedes. That detail matters emotionally and physically. It is moving away without looking away. The near side remains the familiar face, and the far side remains the hidden record, both traveling together. When you see the moon tonight, the change will not be visible. It will look as it has always looked in memory, pale, cratered, sometimes sharp, sometimes hazed by Earth's air. But behind that stillness, the orbit will be fractionally wider than it was before. That is the answer to the title in its simplest form. The moon is slowly leaving us because tides transfer angular momentum from Earth's spin into the moon's orbit. The result is a measured recession, about 3.8 centimeters per year, carried by gravity through ordinary nights. But the fuller answer is gentler than the title first sounds. The moon is leaving only in the language of deep time. In the language of tonight, it is present. In the language of a lifetime, it is steady. In the language of geology, it is moving. All three languages are true. The mistake would be choosing only one. The moon belongs to the child who draws a crescent, the navigator who reads a tide table, the scientist timing a laser pulse, and the future observer who may never see a total solar eclipse. One object, many clocks. There is something profound in that slowness. The moon does not need to hurry to transform the sky. Earth does not need to notice each increment for the increments to be real. A tide lifts, a planet turns, a companion world moves a little farther into the dark. In a strange and beautiful way, the moon's recession makes the relationship more visible. It shows that companionship is not the same as stillness. Two bodies can remain bound while changing each other. They can keep a history between them, written in water, rock, light, and time. The moon is close enough to guide a tide and far enough to be its own world. It is bright enough to enter a room through glass and old enough to preserve events from before animals, before forests, before the continents took their present shapes. Every year measured by laser beams sent from Earth and reflected back from the lunar surface, the moon moves about 3.8 centimeters farther away. That sentence is both measurement and elegy, though the elegy is quiet. Nothing is ending tonight. Something is continuing. And that is why the opening number returns at the end. It is small enough to be held in the hand and large enough to connect the present sky with the ancient one. It belongs to observatories and oceans, to Apollo reflectors and fossil tides, to the moon's basalt seas and Earth's slowing day. The number does not close the story, it keeps it open. A pale disk, a basalt plain, a crater rim, a boot print in dust, a hidden basin, a cold shadow holding ice, a tide under a dark window, a laser pulse returning home, a year, a centimeter, another year. The moon remains overhead, near in the language of space, distant in the language of walking, faithful in appearance, restless in physics. It is not gone. It is going. And the going is part of the bond. We inherit one era of the moon, not all of them. The people before us saw a slightly closer world. The people far ahead may see a slightly smaller one. Tonight we see this moon, at this distance, in this chapter of the tide. It carries every sea, crater, and quiet plain with it. The names, the rocks, the scars, the dust, the reflectors, the old highlands, the hidden far side, the polar dark, A whole world widening its path by the width of a small annual breath. Not a farewell, not a rupture, a measurement, a relationship, a slow widening. The ocean answers, the planet turns, the orbit opens, the archive keeps its pages. Good night.